Thank you. Yeah.
So welcome back. Now we have a presentation by Mr. Alexander Barth. He's an associated professor at the Hydrodynamics and Environmental Research Group of the University of Leeds. He obtained his PhD in 2004 at the on data assimilation in nested ocean models. After his postdoctorate at the College of Marine Science of the University of South Florida, he worked on variational interpolation with DEVA and DEVA-ND, and he's principal investigator of several European projects aiming to apply and improve these tools for generating climatologies based on in-situ observations. Recently, he also investigated the use of machine learning techniques with ocean remote sensing data.
Thank you very much. So today I will speak about denoising diffusion models, how you can train them on incomplete satellite data. So we are interested in ocean properties like sea surface temperature and chlorophyll or altimetry. But unfortunately, a large fraction of the Earth's surface is covered by clouds, which blocks all these optical sensors. And but for many applications, you will need to have full fields. Like even if you compute the mean, you will need to have a full field. If you're just computing the mean on available data, you will bias your mean towards area where we have less cloud coverage. And also another problem is that the accuracy of the interpolated field is not something uniform then. Okay, while you can assume that the accuracy of the input data is often uniform, sometimes not, but often is the case. When you do the interpolation later on, obviously you have much precise results where you have data and less precise results where you don't have data. And here is kind of a motivating example. So what you have on the left is the sea surface temperature as observed by MODIS, which is a satellite from NASA, which and you see obviously you have missing data. You have clouds. This is the white patches there, and that's the Alboran Sea and the Mediterranean Sea. And you have classical techniques like DEVA-ND that can allow you to give an estimate over the full area. But typically, where you don't have data, the analysis would be rather smooth, okay, and also you lose some small scale information. And more importantly, it is really hard from this classical technique to get a realistic area estimate out. So what we developed is to use neural networks for this. So neural networks are really interesting because they are very easily extended to multivariable variables, and also you can also train them on incomplete data. Yeah? Just by applying some scaling, instead of working with the data themselves, we divide the data by the expected error. And if the data is missing, we're just simply saying, okay, the error is infinitely large, so it will give a true zero. Okay? So that's the baseline technique that I will use in my talk, which is called DINK-A, is a typical UNet. So you have your input data, processed with clouds, and then you go through a certain number of convolution layers, and then at the end you will get the actual field, but also the representation of the error. Okay, and this is quite close to what Anas was mentioned yesterday in his talk about surrogate model. So often you ask the model just to give you an answer, but you can also ask the model to give you an answer in the uncertainty. And this is also something that you can include in your cost function. And so the loss function is a bit particular in this sense because you have not only the reconstruction but also uncertainties. So and if you take the logarithm of the Gaussian likelihood, so where y is the actual measurement, yeah, sea surface temperature on the satellite, y hat is the estimated sea surface temperature, and sigma hat the estimated standard deviation. Yeah? And if you write down this conditional probability for the Gaussian, you will end up essentially with two terms. So one term is saying the neural network should be close to the data where you have it. So this is this term, scaled by their expected error variance. And then, again, another term, which is often constant if you don't consider it, but then it takes into account the logarithm of the error variance. Okay? And there's a nice interplay between both terms. So if you would not have this term, yeah, a neural network will just be lazy. If you ask him what is the temperature for tomorrow, it will probably say it will be 10 degrees, but with an error of 100 degrees. Okay, this term would be really small because it says I'm really uncertain about this. Okay, so therefore the second term is there to keep the neural network informative, saying you have to make a decision. You cannot just say you don't know all the time. And so we applied this to seasurface temperature. Here, this is a case from the Adriatic, also Mediterranean Sea, and and it's quite easy to include other parameters that we know that are. Yeah, Anas, you have a question?
Sorry, there was that last term on the loss function, the log of 2 pi.
Yeah, it's a constant. I just put it here for completeness. If you have a logarithm, you get all these 3 terms, but then you compute the gradient, and everything which is constant just disappears. Okay. So when we use neural networks, fairly easy to compute, to use other parameters. So we know that chlorophyll concentration or seasurface temperature is also related to wind stress. If you have a lot of winds, typically temperature goes down. And also fronts in temperature tend to be aligned with fronts in chlorophyll. And so there's a lot of synergies between the different variables. And we were able to show that it actually helps to include these additional parameters in order to make a reconstruction of data. And also we extended this technique to not using structured satellite data. So typically seasurface temperature will essentially be images, so arrays where you have just missing data. But there are some satellite data that just give you just a point cloud. It's actually just a satellite which flies over the ocean and then measures the data along a track. So it's no longer data which is organized along a grid. But by just adapting your first layer in a neural network, you can also include this kind of information and then still get some gridded data along with an expected error estimate in return. So we validated, and it's the validation compared to independent data was relatively good. And also what is quite interesting is that we also can estimate the reliability of the predicted error. So simply by every time when the neural network tells me, okay, for this pixel I have an estimate of saying, so this is altimetry, those in centimeters. For this pixel I have an estimate of 1 centimeter, okay? Now let's take all the pixels where I have an error about 1 centimeter and then compute the actual error compared to independent data, okay? And so if both coincide, you should be perfectly on this dashed line, okay? So what we have, it's a slight offset, but it's still a very good match, actually. So we are underestimating the actual error by 4%, but to me, it's quite surprising that the neural network was able to give a really reliable error estimate. And that is something that's actually very hard to get from traditional methods, because a lot of assumption goes into how the error is. So if you know about optimal interpolation, which is quite commonly used in oceanography, there's a lot of assumption that goes into the how the error is correlated in space, and this will actually give you a usable estimate of your of the variable, of the reconstructed variable, but it will actually not be really reliable on the error estimate. Okay. But there's a big limitation that we have here. So far, we have an error per grid cell. Okay. So we have an image as an input, yeah, with clouds, and we'll get a full image as the output, and then for every grid cell, we get an error estimate. Okay. But as once you do something on this reconstructed image, which involves different grid cells, you need to know how the different grid cells, how the error in different grid cells are correlated. So a very simple example would be just computing the mean. Okay, if you assume that there's no correlation between different grid cells, just computing the mean, it will give you it will severely underestimate the error in your mean if you computed all grid cells are statistically independent. Okay, so it is very important to not only give you the error for each point individually, but also tell how this error is correlated in space. Okay, and in ocean modeling, or in particular in data simulation, so when you combine ocean with ocean model output with data, there's a technique which is commonly used, which is called the ensemble Kalman filter. You're typically not running your model once, but you're running the model several times, yeah? And then the spread of the model gives you the uncertainty, and it also gives you how the different grid points are related. And this is actually what also all the weather services are doing. So today, if you look in your app and seeing tomorrow there will be a 10% chance of rain, it just means that the ECMWF or any other weather service has run 50 ensembles, 50 has run the weather model 50 times with slightly different initial conditions, and in 10% of this ensemble simulation, it was raining. So using an ensemble approach allows you also to take into account this uncertainty. Okay, and we're using here a denoising diffusion model, which is a really as a new type of generative model. It's really fun to play with it. So you can generate images based on text, and they are really good at generalization. So they learn what is the structure in an image, and then you can guide the generation of the image using text. Okay, so I'm pretty sure there is no penguin on an astronaut penguin on Mars in the training data set, but it still managed to combine this information. Okay, and the math behind the denoising diffusion model is actually quite elegant, I think. And so you start with an image, yeah, and then you add noise to it. And you add noise to it just a little bit in a large number of steps. So think of 1,000 steps or 100 steps where you corrupt the initial image with noise. And what you get in the end is a completely noised image. Okay, you're destroying all the information. So that was the easy part. Destroying information is easy, just adding noise. Okay, but then a denoising diffusion model makes the backward steps. Okay, but not from a fully noised image to a realistic image, but only from one step to the previous step. So these are a really large number of steps. Think of it as 100 or 1,000 sub-steps. So when you just add a little bit of noise, the problem gets much easier to remove the noise. Okay, and this is really really profound consequences, because when you generate this image, yeah, and so think of your neural network has 10 layers and you have 1,000 steps. The image generation use effectively 10 times 1,000 neural network layers. So you have a huge neural network, very, very deep neural network with shared weights, obviously, but to generate an image. But when you train the neural network, it will be just from a noisy image with a little bit, removing just a little bit of noise. Okay, so this helps a lot to train really deep neural network, and what is also something called the vanishing gradient problem. Okay, any questions about this? Okay, yeah. Yeah, it's exactly this. Exactly, it's the same network with the same weights. Yeah, it's not, but you give it the diffusion time in some sense. the network knows, okay, now I'm at step 50, and I have to go to step 49. Okay, so it knows at which step it is, but the weights are the same, exactly. Yeah, good question. Okay, and so we trained this on chlorophyll data of the Black Sea. So we used all the data of the Black Sea and then validated on this area. So, and this was the first time we worked on this kind of network. So the size of the image are fairly small. So this is just 64 by 64 grid cells. And as usual, we are training on about some 15 years of data, and then validating on the last years of data. So the validation and test data set is independent from the training data set, as you would expect. Okay. So now the traditional diffusion model works. You train the traditional diffusion model by using complete images. Okay, but for ocean data, you never have complete images. You could use them from a model, but if you want to train a diffusion model, or you could use it from a hydrodynamic model, but if you want to train a neural network with satellite data, you will always have clouds. So you have to think about how to include the fact that you have missing data already in the training data set. So what we use, we have this original data with already some clouds. Okay. We add even more clouds. We're just taking the cloud mask from another image, and so we have this image with combined cloud. Okay. And then everywhere where you have cloud, we replace the values by just noise, random noise. So meaning something is clouded, it's just saying you don't know anything about it, so it is just a noisy, a random variable, instantiation of a random variable. Okay. But in fact, when in traditional diffusion models, you assume that an image, yeah, is as a fixed state of degradation. Yeah. Here we assume that every pixel can be a different state of degradation. Okay. So you have some pixels here which are non-degraded at all. They are in fact already very at the start of the diffusion pipeline, and one are completely degraded, and one are just partially degraded. Okay, so that is the trick that we use to train the neural network with noisy data, is assume that every pixel can be a different state of degradation. Yeah.
I find this really interesting. So usually with the diffusion, you're adding noise to corrupt each time, but it seems like one of the things that can be done here is like the actual cloud mask itself could be the noise that corrupts the original. Because the goal is to take an image that has cloud cover on it and recover the original image without the cloud cover.
Yes.
And so instead of corrupting it with noise, are you corrupting it with a random cloud mask every step? Is that what's happening here, or?
So the additional cloud mask, that's just added once. Okay. Well, it is, and then when you go back, when you do the reverse diffusion, this cloud mask doesn't change. Okay. So in this step, it is fixed. Okay. But during training, you will make other combinations. Okay. And so the idea is that you have this image, and then you have a different noise level for every pixel. Okay. And then you are asking the neural network to remove the noise. Okay. And the loss function, you can only evaluate them at the pixels where you have the ground truth value. Okay. And so when you have your neural network trained, then during inference, you take this image, every cloud is replaced by random noise, and where you have actual data, you're saying these pixels are already totally uncorrupted. Okay, these are already at the step 1 of my reverse diffusion pipeline, and the other are at step 800. Okay, and then you're asking to go just one step back. Okay, and so on, and then you will see that naturally a realistic looking image emerges, because you're asking for every pixels where you have some noise, just remove a little bit of noise. Okay. And so, and the nice thing is once you have an ensemble, you can always compute the mean and things like standard deviation. Obviously, when you compute the mean, you will smooth out all this fluctuation. This is actually a desirable property. If you ask me what is your most likely estimate for chlorophyll or for temperature, then, and if you have an ensemble, then you should take the mean, okay? Because this minimizes your error. But once you have this sample, you can easily now use this sample to compute other statistics as well, like the standard deviation, or other some derived quantities, like if you're looking at fronts and things like this. So you can easily propagate this uncertainty in a Monte Carlo-like fashion to other approaches. Okay. And so there are different ways that we can validate this result. So we're looking here at the variogram, which tells you essentially how similar the field is between two grid points. Yeah? And if this distance between two grid points goes to 0, the variance between them should go to 0 as well. So that's the variogram. And it's how quickly they go to 0 tells you how much information you have at small scales. Okay? And we see here that in blue is original data. In orange, that's the Dinkai data, so the traditional UNet. And we see that we're losing a lot of information at small scales. But with the diffusion model, we can actually recover a lot of this variance. It's not as variable as original data, but it's already much better. Another thing that we can do is actually, and this is done quite often in metrology as well, is to compute the talagram diagram, and it essentially tells us how reliable your probabilities are. Okay, so if I say the probability that the chlorophyll will exceed a different threshold by, say, 20%, can I trust this 20%? Or did you make it just up out of thin air? So how reliable this estimate is, okay? So the talagram diagram is a bit mathematical, but if you, there is a graphical representation, if you have a flat talagram diagram, it means that you are, so if all these blue arrows will be the same height, and then it means that your probability are perfectly reliable. Okay, and here we are not actually too far away from it. We're quite happy about it. So you can easily think of if you have hundreds of an ensemblement of hundreds states, yeah, and you took the median state, yeah. And then your actual measurement should be 50% lower and 50% higher than the median state. Okay? And so what the talagram diagram is just not losing the median state, but it uses all of these quantiles for every ensemble member. Okay? And just this is an example with Dinkai, which can also provide an error estimate, but it's not, so the diffusion model is really much more reliable in terms of the accuracy of the ensemble. Okay, so here this is just an animation about where I applied this technique to a larger data set, which is modices for temperature for the whole globe. So it's trained really on the whole globe, and I here use larger images. Before it was 64 by 64, now 125 by 125 to give more context to the reconstruction. So what you have here is the original data, and then the data where so original data with some clouds. In this case, quite few. And then we added even more clouds because we want to know how the method is actually doing. And this is the data were replaced by noise. And then we're asking the neural network to, during this reverse diffusion, to at every step reduce a slightly bit of noise. And then we have a quite realistic looking image at the end. And it's not only realistic looking. When you compare it to really quantitatively with RMS error, you will see actually it's actually better than Dinkai. Yeah, Ines?
So just to kind
Mhm.
and then that mask allows you to add. You can only add noise where the mask is. You don't add it anywhere else.
Yeah, during inference, yeah.
And then you go through your diffusion steps and corrupt it, and then you go backwards, and then you pull away the noise and which the mask doesn't exist anymore. Only the noise does, because
Yeah.
the mask only says where the noise should be.
Yeah, exactly.
And then when you go backwards, you decorrupt it by
Yeah.
denoising it.
Yeah, exactly. So the mask tells you how where you should put the noise. Yeah, exactly. Okay, so in conclusion, we had another question, no? Okay, so in conclusion, so I showed two methods. So the Dinkai with a traditional UNet, it is trained in a classical, I would say classical supervised way. You have your image with noise, with missing data, and then you add even more missing data and then try to recover the data under the clouds. And the diffusion models actually gives a better accuracy than Dinkai, and it gives also a reliable ensemble, so which is also statistically reliable. And this was quite interesting to see actually, that you can actually trust the different ensemble that is produced. And this is quite important in order to propagate uncertainty. So you don't, so somebody who wants to use the satellite product later on, okay, instead of using just the ensemble mean or just a single reconstruction, the idea is that any other processing step which comes later will also operate on different ensemble members, and then you naturally get also an uncertain estimate of the output. Okay, so if you want to identify fronts, okay, in some ensemble members the front is maybe slightly offset, and then later on you can see, okay, in some places the front was always located in this location, so the uncertainty in my front estimate is quite low. But in other cases, the front is shifted, so this can also be represented. And also, really nice thing that you can, you no longer, you can, in the ensemble members, you can retain small scales. They're not smoothed out. If you take the mean, obviously it will smooth out because you don't have information about small scales in the actual data, but every ensemble member individually contains this small scale information. And so we have two papers here where you get much more information, particularly if you're interested in the more information about the validation. And everything is on GitHub and written in JuliaEO. And so just to set the stage for what's coming later on, so I made some toy models about ocean modeling, and I don't know about you, but in our university, it's not always easy to motivate students to get interested in ocean modeling. And so I made some animations, or they're actually demos, so that run in your web browser. That's actually Julia code, which is compiled to WebAssembly, and then we can run it directly on your web browser. And you can. This is, I think, something I showed already last year. So you have a flow which goes from the left to the right, and then you can perturb this flow by adding other islands to see how it changes. And something what I made recently. So this is a simulation of the equatorial ocean. So the equator is really you can think of the equator as the middle line in the ocean. So this line would be the equator, and you have an initial perturbation. And what happens at the equator, very interesting thing happens, that this initial perturbation breaks down in two different waves. This is a Kelvin wave, and this is a Rossby wave, and this is the driver of, for example, the El Nino weather phenomenon. And you can also play around here. You can say, let me perturb this Kelvin wave by a coastline. And you see, so if an equatorial Kelvin wave hits a coastline, actually it splits up, and one is going northward and one's going southward. And this is essentially due to the Coriolis force. A lot of things which happens in the ocean, which are really a bit counterintuitive, it's due to the Coriolis force, and it's a really quite interesting thing. Yeah, and so there are other models here that I just implemented. So this is smooth particle hydrodynamic models, and it's also implemented in pure Julia. And then you can actually WebAssembly is a support backend in Julia, and then you can compile it down to WebAssembly. But it's a bit tricky because only a small subset of Julia is supported in this way natively. Yeah, so if you want to play around this is the URL, tiny URL/model font, so it's easy to remember. Yeah?
I'm curious though, for like, for example, with the Grayscale model, I saw in there, like the Grayscale model is a classic, like, diffusion kind of one where you normally would want to use implicit methods, but I assume that you wouldn't be able to compile anything with loss too well, right? So how did you handle that part?
Yeah, so I actually tried to compile BLAS into WebAssembly. It's just a nightmare. I did not succeed it, and it's really, really difficult. And so I used an explicit scheme here. Yeah.
Okay, so they're all just explicit schemes.
Yeah. But actually, in this case here, and so these are the waves, the surface gravity waves in the ocean. And if you, for example, so this is the external wave, yeah. And if you are just having a look at the other wave number, what you see here are the internal waves. So if you remember Giles' simulation about the internal waves, yeah. So this is the typical vertical structure of the internal waves in the ocean. So this is a cross section. So one dimension is the horizontal dimension, one is the other, the vertical dimension. In order to compute this, you need to compute the eigenvectors of a matrix. And yeah, that was the reason why I tried to compute BLAS to WebAssembly, but it's really difficult. So I use a very simple scheme. Yeah?
Similar to your previous tool, I think for DIVA demo, you also had a web page to play around with DIVA.
Mm-hmm.
My question is related to that. How do the previous models you showed in terms of the diffusion model and also the convolutional model, how do they kind of compare to DIVA and D?
Okay.
And also maybe comment on the performance of all these models. How long does it take to train? How long does it take to run?
Yeah, very good question. So the DIVA-ND model is a kind of classical model, and it is much faster. Doesn't need a GPU, and is, I would say, quite robust. But it's not easy to incorporate, for example, other parameters. So it's difficult to do a multivariate analysis with it, and the error estimate is not so good that you get. The error estimate is just a way to say, okay, in this area, the error is so big, I probably should not show it at all. So it is, it's rather used for masking. So the neural network, takes much more time, and it also needs much more data as well. Okay, so if you have a lot of data, I think it's worthwhile to try the neural network approach. But if you have few data, and I think it's better to use DIVA-ND, classical method. Okay. Yeah, Anas?
Not related to the images, but just to the diffusion model. I noticed that with the folks here, that the common problem is there's real data, but it's not enough scale that you typically would need to like train a large neural network. And so in those kinds of scenarios, typically what is usually done is you find some kind of useful auxiliary task. You can kind of sample data from freely, and then once you train something, you kind of use that as a backbone and then fine tune. And I was thinking about the masking you were showing earlier approach. And what I find fascinating is that you have the image, you add a mask, and you only add noise where the mask is. But curiously, there are different variations of diffusion models where you don't corrupt with noises, but you corrupt with special kinds of masks. And what came to my mind was that
Yeah, that's true. That's true. And there's I've seen one paper who mentioned that the task of corruption can be very generic. So as you manage, you can corrupting by adding clouds or any other corruption task actually can be used in the diffusion model. And it was indeed when you're working with incomplete data. It is actually quite natural to consider the cloud coverage itself as the corruption. Yeah, yeah.
Yeah, and it seems like it's a great starting point because you don't have to rely on real data to start your training. You can take some kind of basic simulation of temperature distribution or whatever it was that you were interested in,
Uh-huh.
and then use that as a starting point. You can easily corrupt it in the natural way that you would expect to understand the problem, which is that there's how clever it's corrupted and you need to remove it. You can do that over
Yeah.
time. And then it removes your data problem because technically you have a simulator that you can query for free and have a good strong starting point, have a starting kind of understanding of what the modality is, and then with real data you can then fine tune and not necessarily need that kind of large scale that you typically need if you were to start from scratch.
Yeah, that's true. That's true. So transfer learning can help a lot here. So I tried a bit this approach to see what you can do only using data. So not to because the result later on sometimes will be compared to a model, to validate a model, and sometimes you don't want to have this kind of inbreeding where the what you call data is actually also influenced by model. So sometimes you would prefer it to have so separate.
But in the fine tuning case, you would not use a simulator as a validation. You would actually take your data and split
Yeah,
it and then
yeah,
only use it. So
yeah, that's true. That's true. Yeah, yeah, Chris.
Yeah, I was wondering if you go back to your slides.
Sure.
If you go a few slides back, yeah, okay, one slide forward again. Right to this kind of conclusion here, right? So I want to go back to reliable ensemble of possible reconstructions and propagate the uncertainty, right? How do we know that that's actually reliable? I mean, because here's my real question here, right? So when we're learning functions, say with the neural network, right, we're guaranteed to have some sense of, if you have enough data points, this is going to converge you pre-approximating the function, right? Now in this context, you have something that's generative, right? And it's generative in a way that is giving you probabilistic results with some uncertainty, right? Do we have any guarantee that as we get more data points, that uncertainty that it is converging to actually has the same exact probability distribution as the uncertainty from the actual model, or is there no sense of that guarantee that it's actually giving you the exact same probability distribution, just one that maybe looks empirically like it?
So actually we validated the uncertainty empirically using this telegram diagram. Okay, so just by having this ensemble of reconstruction, yeah, you can see you can essentially you order your ensemble members from smallest to largest, and then you look where your observations fall into. Okay, and then you increase the count for every bin. Okay, and if your ensemble is well behaved, is reliable, yeah, you should fill all the bin equally. Okay, so this is a graphical way to represent the.
And I followed you through this to say that, empirically you're able to show that this method is able to in this context, seems to reproduce the uncertainty, right? My question is, but do we have a theoretical guarantee that this method, if you do have enough data points, is supposed to actually converge such that the probability distribution is the right one, right? Not just empirically, but do we have like this convergence proof to be able to say, and I know that if I have enough data, it's actually supposed to have this property.
Mm-hmm.
yeah, that's in the original paper for diffusion models. They walk through the process that in the limited data, recover the original modality of distribution. So it's part of the diffusion formulation.
Yeah. So. If we have a theoretical proof, so there are some assumptions in the diffusion paper. So the actual cost function that you want to optimize is not tractable. So they're computing something like a elbow lower bound value of this cost function, and they're using this. So there are some approximation into it. And but intuitively, I think when you give what you want to have is the field with less noise, yeah? And by applying this denoising process, in the optimal sense, so if your neural network is really optimal, it should really span all the probabilities. Right? Because if it does not span all the probabilities, yeah, it's not really really optimal. It's not really it did not really the right thing during the denoising. But really, for mathematical hard proof, unfortunately, I have to pass.
I'd just be scared to kind of take this and say, you know, when you say reliable uncertain propagation, I would think that you mean like, oh, you have an unbiased estimator, right, in the statistical sense, right? And for me, it's kind of hard to kind of make the jump and say, oh, I believe that this is an unbiased estimator, right? I believe it's an estimator of uncertainty, right? It gives you some kind of measure of it, but to know that it's an unbiased estimator, I think is a bit of a jump.
Yeah, yeah. So mathematically, it's not. I cannot. I don't know if it's really proven mathematically, but empirically, so we're using this telegram diagram, and in the paper there's another score that we use, the continuous rank probability score, which is also used in meteorology, where you can estimate the probability. But in practice, when you're doing weather forecasts, there is no mathematical proof either that your weather model will give you all the range of possibilities, simply because you don't know what is the uncertainty, the true uncertainty in the initial condition. You're just knowing from experience that well, when I start my model with this kind of initial condition, I should also perturb in a different way because my initial condition is not perfect. So practically, there are a lot of other things that we don't know exactly about uncertainty. Okay, thank you so much.
Thank you so much. Up next, we have a presentation by Mr. Simone Silvestri. He did his PhD at the Delft University of Technology in the Netherlands, where he developed a GPU-based tools for direct numerical simulation of high-temperature turbulent flows and studied the influence of different heat transfer mechanisms on turbulence modulation. He is now a postdoc at the MIT, where he is developing a new generation ocean model within the Climate Modeling Alliance project.
Is this working? Okay. Yes. Okay. Well, hello. I'm Simone. As I was introduced, I'm a postdoc at MIT, where I work with the Clima project to develop a neural system model in pure Julia. So the Clima project is a collaborative project between Caltech, MIT, and JPL that has the objective of creating a new climate system that aims to reduce the uncertainty in future climate projections. And particularly at MIT, we are developing the ocean and sea ice component of this model, which is called Clima Ocean, that leverages the Oceanigans library, of which I'm one of the main developers. So today I want to present a little bit our packages, but I would like to start with a little bit of an excursus on why the Clima project is trying to develop a new climate model. And this all has to do with the difficulty of predicting future climates. In this plot over here, I'm showing the projections of global surface air temperature as predicted by several CMIP class models under two different scenarios. So the yellow lines are a high emission scenario, while the blue lines are a low emission scenario. And the first thing that we can see from this image is that the predictions of global surface air temperature are quite uncertain, because the 2-degree threshold is predicted to be reached by the different models in a time range of about 2017 to 2017. So there is a very large uncertainty on these projections. And when we look at an image like this, we have to keep in mind that this is a quantity that is quite easy to predict for a climate model. So this is global surface temperature anomaly. There are other quantities such as precipitation or extreme events or local extrema that are much more difficult to predict and do impact human life. So they will carry a lot more uncertainty. So there's a lot of work to be done. But this is not to say that climate models are necessarily bad. Climate models are very sophisticated machineries, and I think that they're very advanced softwares. It's just that climate prediction is a very hard task. And it's hard for two main reasons. So the first one is that our tolerance for error is extremely low. So we are trying to predict a signal that it's about 3 to 5 watts per meter square in average, when the Earth system is forced instantaneously by fluxes that have value upwards of 1,000 or 2,000 watt per meter squared. So basically, these very complicated machineries have to predict consistently a very, very tiny residual and have to do it very well for hundreds of years to be able to do accurate predictions. And this in itself is a very challenging task. But probably the main problem of predicting climate is that climate dynamics are intrinsically multi-scale. So there are processes that influence climate, and we cannot really think to include all these processes in a computational model, particularly because some of them are just too tiny. So some dynamics are just too tiny to be represented on a discrete grid. But also for some processes like cloud formation or rheology of sea ice, for example, they're so complicated that we don't even have first principles equation to describe them. So the reality is that in climate modeling, we rely extremely heavily on parameterizations. And these parameterizations are characterized by free parameters that really hold most of the uncertainty in climate projections, because they are typically hand-tuned. So Klima has a plan to try to solve this problem, and this plan has two parts. So the first one is let's say the brute force approach. So what we want to do is want to try to increase the resolution of climate models as much as possible, because if we do this, we can eliminate the most uncertain parameterizations in the climate model. And the second strategy is to leverage as much data as possible to do a global calibration of all these parameterizations together in a global context. So atmosphere coupled with land, coupled with sea ice, coupled with an ocean, and try to estimate these parameters from data. And already this is a huge computational task. So since we're doing the ocean, I would like to frame a little bit this problem in an ocean framework. And I'm showing here the main processes that influence climate from the ocean, broadly subcategorized in the length scales. So the largest dynamical process is large-scale circulation in the ocean, and this has length scales of about 2,000 kilometers. And this is directly solved by basically all ocean models. And then we have all the turbulence processes going down to 1 meter scale. So in particular, we have a mesoscale turbulence, that is basically those large geostrophic eddies that are caused by a balance between pressure gradients and the Coriolis force, the rotation of the Earth. And these eddies are responsible for most of the lateral heat transport in the ocean. We have some mesoscale eddies, which are basically the same type of eddies, but are constrained in the mixed layer, so only in the first 100 meters of the ocean. Going down all the way to boundary layer turbulence, this is the classical non-hydrostatic isotropic turbulence that has scales of 1 meter. That's characteristic of convection in the upper ocean, bottom boundary layers, or even internal wave breaking. So the first thing that we want to do, following the Klima strategy, is to increase the resolution as much as possible to directly simulate these processes. And we have no hope whatsoever to reach the meter scale in the ocean. That is not possible now and is not possible in the future, because a climate model that has a 1 meter resolution would necessitate 10 to the power 20 grid cells. So that is completely unfeasible. But with the technology that we have today, we can think about a model that has a resolution that is large enough to at least encompass mesoscale turbulence. And this for us is very important, because mesoscale turbulence is one of the most uncertain processes in the ocean. So it's very difficult to parameterize because it's extremely non-local. So basically, developing parameterization for mesoscale have frustrated generation of oceanographers. So if we're able to resolve it, then all of a sudden we reduce significantly the uncertainty in our projections. Then for the other processes that we cannot possibly represent in the model, the idea is to have a software that is flexible enough to be able to solve all these dynamics in smaller patches, so that we can generate reams of synthetic data that we can use to constrain the parameters of the parameterization that we will use in the global model, or at least give us some priors that we can use to then calibrate our parameters in the global context. So this approach really sets the requirements that we need for our new generation ocean model. First of all, it has to be computationally efficient because we want to increase the resolution, and because we want to calibrate the global model at high resolution, and this is a very, very heavy computational task. But second of all, the model has to be flexible and easy to use, because we want it to be able to represent all different physical processes, and we want to have a playground where we can really plug in and test different parameterization, different ideas, and calibrate and see what works. So the big question is, why are we writing a new ocean model? Because writing an ocean model is a very, very complicated task. It's kind of an effort. And arguably, we could have achieved the same goal by just improving an existing ocean model. But we believe that rewriting the model from scratch has its own advantages. And this is because since ocean models are very complicated, they have a lot of inertia. So ocean models have lagged behind at least 10 years with modern CFD software. In particular, basically no ocean model, there are a couple, can use GPUs. So no ocean model is written to make efficient use of GPUs. And this is a big disadvantage because GPUs the use of GPUs is growing in the computational community. Second of all, since all ocean models are written in low-level programming languages like Fortran, the user interface has changed little to nothing from the 80s. So here I'm showing an example of the Cox model from 1984. And this is a nameless user interface, which is basically similar to any other ocean model that is available today. And that's why probably Gael and Alexander are developing Julia wrappers to try to make interacting with ocean models easier. So we kind of want to change this paradigm. And third of all, most ocean software has a very limited scope. So it's either LES models or regional models or global ocean models. And a notable exception is the MIT GCM that Gael showed before, that can cover all these regimes and probably has to thank this flexibility for its widespread adoption. So we believe that writing a software from scratch, we can really address all these points and create a modern software that is written with higher-level programming languages that can use efficiently the GPU and that can achieve high resolution. So in general, this is our vision, having an accessible and extensible and productive software. Okay, given this introduction, I can finally start talking about our packages. So first of all, this is a quite large collaborative project. So I put here all the developers or the main contributors to the code base. So Greg and Navid are part of the core team, and then there are all the other people that helped with advising or contributing to the code base. So first of all, it's important to understand the distinction between ClimaOcean and Oceananigans, because I already received this question in this conference in past days. So Oceananigans is a library for idealized and realistic fluid dynamic simulations. And idealized simulation come in all shapes and sizes. You can do pretty much everything. But realistic ocean simulation tend to be a little bit more narrowly defined. So typically you need a bathymetry, you need a forcing that can come from a prescribed atmosphere. You need to compute fluxes of water vapor, of heat, of trace gases. You need to initialize the model with realistic initial conditions that typically come from climatology, and sometimes you need to relax your model with the same climatology. So you can do all this only with Oceananigans, but it tends to be a little bit cumbersome. So it's all about that data wrangling. So we are developing ClimaOcean to kind of fit these requirements. basically, ClimaOcean is a wrapper around Oceananigans that uses Oceananigans and ClimaCIs, that it's our CIS model, to construct realistic ocean simulations that fit all these requirements. On the other hand, Oceananigans is the library behind the model. So Oceananigans implements all the ingredients that you need to build and run a fluid dynamic simulation. So it has all our discretizations, spatial and temporal. All the physics is in Oceananigans, so all the parameterizations are written in Oceananigans. And also all the utilities that are required to actually build a simulation, to run it, and to analyze it. So the blueprint for Oceananigans at the beginning was the MIT GCM that Gail presented before. So like the MIT GCM, also Oceananigans works in a finite volume framework on a staggered C grid, meaning that the velocities are at the face of the cell while traces are at the center. And it works on locally orthogonal grids with Cartesian and spherical domains. So I would like to start with diving a little bit in the user interface of Oceananigans, which it might seem trivial to all the Julia experts around here, but we believe that the fact that we have a programmable user interface really distinguishes Oceananigans from other ocean models. Really is the real advance of our package. And this is because all the ocean models are written with this monolithic name list type of interfaces that kind of curb the flexibility and the usability or extensibility of the model. So it's very difficult to become creative with a current ocean model. While Oceananigans, leveraging Julia, allows you to have a programmable user interface that can extend. Basically, Oceananigans users are Julia programmers that write scripts that use Oceananigans to build and run numerical experiments. And this is definitely allowed by the Julia language, but we also put a lot of care into designing the user interface to make sure that it's very easy to interpret and to use. So our goal is that oceanographers that have no idea of numerical computation can take Oceananigans and understand what's written in a script and understand what the simulation does. So there's a lot of tweaking that we do to make sure that we achieve that goal. And to give you an example of this, I want to show you a very simple simulation in Oceananigans. This is taken from the README of the Oceananigans repo. It's the simplest simulation that you can do in Oceananigans. It's basically a flat domain that is periodic in 2 directions, initialized with a random velocity field that then eventually develops turbulence and decays. And it contains all the ingredients that you need to run a simulation. So Oceananigans builds a simulation object on top of a model. In this case, this model is a non-hydrostatic model, which means that we're solving the incompressible Navier-Stokes equations. Because in our language, a model refers to the set of equations that you're solving. So in Oceananigans, we have the non-hydrostatic model that solves the incompressible Navier-Stokes equation, the hydrostatic free surface model that solves the primitive equations with a free surface, and the shallow water model. And all these are abstract models. So it is possible to subtype an abstract model in external packages and leverage all the implementations that we have to make it easy to run a simulation with a simulation object. So this is what we do in the ClimaCIs package, where we implemented a CIS model, and in the ClimaOcean package, where we implemented the Ocean CIS model. And typically, a model is built on a grid. So in this case, this is a rectilinear grid that tells you that we're running on a Cartesian domain that is 2 pi in length in the x direction, 2 pi in length in the y direction, and has a topology which is periodic in 2 direction and flat in the third, but I cut out the third one here so you don't see it, but it should be periodic, flat. Okay, so the nicest thing of Oceananigans, I think, is that it is super easy to run on different architectures. So by just changing that argument there in the grid, that CPU argument to GPU, this whole code, without changing anything, would run on CUDA-enabled GPUs. And this is because we developed the package on top of kernel abstraction, that is the package developed by Valentin, which makes it super easy to just write a kernel that is architecture agnostic. So in Oceananigans, we really don't care about what architecture you're solving the problem on. We write a general kernel that that can switch from CPU to GPU just by changing one argument. So props to Valentin for developing kernel abstraction, or the Julia GPU folks for allowing this, because we did nothing. We just took what was there. And we also aim to make distributed computations as easy. There's a little bit more complication in that, but as for changing from CPU to GPU, to make this simulation run on distributed architectures, you just change the architecture argument to a distributed argument, and that will run on distributed hardware. Now, it's not as simple as switching CPU to GPU, because with distributed, we leverage the MPI package. So there's this extra complication on making sure that MPI is configured correctly, that in this case you have a CUDA-aware MPI, that you launch the Julia instance with MPI run or srun or whatnot. So it's not as easy, but we strive to make it that easy. So in general, our idea is that the script should not change. Only one argument should change to have distributed computations. This all clear? Any question? Okay. Now, we don't only have to build and run a simulation, we also have to analyze it. So in Oceananigans, we implemented a whole set of a syntax to build diagnostics, to build and compute diagnostics. So basically what we did is we extended the concept of binary operation, multi-operation, derivatives to work on the fields of Oceananigans, which basically are the variables of Oceananigans. And these abstract operations basically build lazy trees of operation that then we can compute. And in this case over here, I'm computing the vorticity in the simulation. So it's just a derivative of the v velocity in the x direction minus the derivative of the u velocity in the y direction. And we can compute this and just plot it with Mackie, and you get something like this. Now, you could say that this is just a two-dimensional simulation, so it's rather easy. I mean, you could do it probably in 100 lines in Julia. It's not that complicated. But it really has all the ingredients to run a simulation. So going to a state-of-the-art LES simulation, there's not much difference. So in this case here, I'm showing an LES simulation that computes the boundary layer deepening in the upper ocean, given a wind stress and a Stokes drift, so some waves that mix the upper ocean. And the script is not that different from what we saw before. So the pattern is really the same. We still have a simulation that is built on top of a model. And we have a grid that in this case is on a GPU because it's a tad bigger. It has 256 cells in each direction. And we just have to add some physics. So in this case, we add some boundary conditions because we have to have a wind stress pushing at the top, at the surface. And in Oceananigans, we can build boundary conditions as abstract arrays or functions. And in this case, we're just passing a function that is a function of time, so wind stress that decays in time. We're adding a Stokes drift, so basically some waves that decay with a vertical coordinate. And we're also adding a Coriolis force, which in this case is an F-plane, so it means that the Coriolis parameter is constant throughout the simulation. And a buoyancy model. So the buoyancy model refers to the equation of state and to the gravity term in the momentum equations. So in this case, we're just passing a buoyancy tracer to the model that represents the buoyancy in the system. So basically, running the script, you get the data that I'm visualizing here on the left. Not so different from the two-dimensional turbulence. So I think it's important to see why this pattern allows for very easy extensibility. So in the examples that I showed before, you can see that in the model construction we have hooks that you can change with different numerics or physics that correspond to the individual terms in the equations that we're solving. So in this case, we're specifying a momentum advection, a Coriolis term, and a closure, which is another term for parameterization. And these types will be propagated inside the kernels, and will tell the specific functions that calculate these terms how to calculate them. So it is pretty easy to build a new type that you can pass to the model and extend these individual functions to create a new parameterization that will work out of the box with Oceananigans. And I'll show here an example of how you would actually build a new parameterization for Oceananigans. So in this case here, I'm specifying a new type that defines a diffusive parameterization. So if you want to write a parameterization as a diffusive process, we already have an abstract type in Oceananigans that, let's say, captures the behavior of a diffusion process. So it's enough to subtype that abstract type, extend a couple of functions, just 2 or 3 functions, and then you have a parameterization that is compatible with Oceananigans directly. And I mean, this might seem trivial for all the Julia people, because this is basically a pattern of the whole Julia ecosystem. But for ocean modelers, it's extremely important to have easy accessibility to new parameterization development, because there is a lot of work in the ocean modeling community on new parameterizations. And the problem comes when the modeler wants to integrate their newly developed parameterization in GCMs or in ocean models. And typically there's a time lag from development to adoption of about 10 years. And this really has to do with the difficulty of putting your hands in the source code, in Fortran source code of typical models, and try to make your parameterization work with that source code. And we really, our goal is to try to shorten this time. So we believe that with this pattern, we allow people to test their ideas, also in their scripts. You can just import Oceananigans, develop a new parameterization, and once it's optimized and validated, you can insert it in the source code with no effort, basically. So this is very important for us. Now, I want to spend a couple of words for ClimaOcean. So ClimaOcean really is just a wrapper. Yeah. Mm-hmm. So we have, I didn't show it in here actually, but there's an extra function you have to extend. It's called compute diffusivity. That compute diffusivity takes the model as an input. So you can build all your kernel that you want. You have access to the whole model. You can compute the diffusivity, and then you don't have to touch the functions in the kernels, because you just compute diffusivity, and then the model will take the diffusivity and calculate your diffusion fluxes. So yeah, that's how we would extend the diffusion process. Okay, so building a global simulation is a little bit more complicated than a non-hydrostatic LES, and it really all has to do with data wrangling, because in a realistic ocean simulation, you need a bathymetry, you need a forcing, you need climatology, you need to download it, you need to interpolate it, you need to regrid it, and it's a mess. So ClimaOcean was born really with the idea to streamline all this process and make this as easy as it is in Oceananigans to do a 2-dimensional turbulence simulation. So here I'm showing again an example from the ClimaOcean README, and this is our counterpart to Oceananigans turbulence in 7 lines, and I like to call it a GCM in 11 lines. And in particular, this is a quarter-degree simulation of the ocean, forced by a prescribed atmosphere that comes from the JRA55 reanalysis product. And the pattern is basically the same. So we have a simulation object that is built on top of a model. In this case, the model is a coupled model that couples an ocean simulation to an atmosphere, and the atmosphere is a prescribed atmosphere that is taken from the JRA55 data. And we also have utilities in ClimaOcean to initialize your model with climatology. So in this case here, we're initializing the temperature and salinity of the model from the echo data that Gael showed this morning. And we have the same utilities for regrading bathymetry. So with this function, you will download automatically the top of bathymetry and regrade it on top of the grid that you have specified. So this really streamlines how to build and run an ocean model. And in theory, it should make it easier. So we'll see an example like this later on this afternoon. A smaller example, because this is a little bit computationally expensive, but we'll see where we get. So this was all to talk about the flexibility and usability, which we believe that is one of the most important parts of the project. But we haven't touched yet the speed, which is also a very important part of the project. So Oceananigans and ClimaOcean are very, very fast. And there is really no secret on why they're fast. They're not fast because we're incredible programmers that discovered a method to do stuff that people haven't thought of. The whole performance comes from the fact that we use GPUs and we use the Julia language. So GPUs are perfect for CFD simulations because they're intrinsically parallel. So CFD is basically a set of very simple instructions done on a huge parallel grid. So GPUs are extremely well suited for CFD. So just by coding efficiently for GPU, we can achieve the speed, incredible speed up when compared to state-of-the-art ocean models. We also care a lot about memory leanness. Yeah. 512 GPUs yeah, this sounds like a lot, right? But this simulation is as big as the one that Gael showed that used 70,000 cores and did 1 year in 3 months. This does 1 year in 1 day on 512 GPUs.
But my experience is that GPU clusters will get.
Oh yeah, they have. Promoter has about 5,000. Yeah.
Just to get an idea of the scale, what GPUs are we talking about?
800. Yeah. Scientific computing GPUs, so 800s. This was computed on 800s. Yeah, so we also care about memory leanness. So 512 GPUs seems like a lot, but it's much less than 70,000 cores. And this is because we really want to run a set of simulations in parallel to calibrate parameters or to explore the parameter space. So we really care that the model doesn't really take so much resources. And this work really paid off because if you consider that 10 simulated years per day is the threshold for a model to be useful for climate projections, because if you do anything below that, then the model is not really useful. We achieved this goal we achieved this threshold on a 16-kilometer resolution on 8 GPUs. So this is a 1/6 of a degree ocean model that can be run on basically 2 computational nodes. But most importantly, we achieved this threshold on 8-kilometer resolution on 64 GPUs. And we care a lot about this 8-kilometer resolution figure because this is a 1/12 of a degree, which is considered to be a resolution at which mesoscale turbulence is completely resolved. So this means that with 64 GPUs, we can run at 10 simulated years per day, a model that is completely mesoscale resolving, and we don't need to use any mesoscale parameterization. So in theory, we are able to significantly decrease the uncertainty in the model by running at this resolution. So I also pushed the resolution a little bit higher. So this 2-kilometer resolution is twice as big as the simulation that Gael showed. So albeit the simulation Gael showed had CIs and saved data, and this is mainly a test for the performance of Oceananigans. But we run that simulation on 32 GPUs, 800 GPUs, achieving 0.1 simulated years per day, meaning that in 10 days we would have done a full year of computation at 2-kilometer resolution on 32 GPUs. Comparing it with the 70,000 CPU cores that were used in the LC4020, that means that one 800 GPU is equivalent to about 2,000 to 4,000 CPU cores, which really shows the power of using GPUs for CFD computing. But another advantage that we have when using GPUs is that we can use high-order numerical methods. This is kind of a little bit of my passion. But the fact is that these numerical methods are prohibitive in CPU computing because they are very expensive. But on GPUs, where most of the cost is just fetching the memory, computations are relatively free. We can really use these class of methods that are very nonlinear, and we don't really pay the full price for it. So in Oceananigans, we have decided to give a shot to Wino methods. So these are very nonlinear reconstruction methods that were developed in the field of compressible high Mach number turbulent flows, where modelers have the problem of resolving shocks. So in high Mach number flows, you have spontaneous development of shocks that are definitely subgrid scale. So you need a numerical method that is capable of preserving grains as much as possible without really propagating dispersive artifacts that will crash the simulation. So you want to maintain your simulation stable, but do that while preserving grains as much as possible. And this is what this class of schemes do. So we think that they're very appealing in the regimes that we want to study, because we're going towards a mesoscale resolving ocean model where you really want to keep as much kinetic energy as possible, because you want to resolve the turbulence as much as possible. So you don't want to lose effective resolution. You want to squeeze as much resolution as possible from your grid size. And this is what these class of schemes allow you. They allow you to maximize your effective resolution given a certain grid size. And we really tried these methods out in a real ocean. So I really want to show an example to show how striking is the difference when you change a numerical method in a turbulence resolving ocean simulation. So this is the Gulf Stream that I've simulated a year back, I think. And the top one is using standard numerical methods that you would use in an ocean model. And the bottom one is using a high order WINO scheme. And to me, it's striking how different this solution looks like. Like the Gulf Stream is not even at the same position. It kind of bends down a bit in the high order WINO simulation. And the currents are much more energetic, much more sharper, and there's much more grid scale eddies, small scale eddies that survive. And yeah.
Yeah, I mean, they do look very different, but it's also in a chaotic scheme, right? So
Mm.
how can you convince me that the second one is also not just a shadow trajectory? Because I would look at the first one and say, okay,
Mm.
there can be a difference between these two because they both just be shadow trajectories of a same chaotic system, right? But how do I know that the second one is actually more accurate rather than just a different shadow trajectory?
Yeah, that's so. I'm showing the spectra on the left-hand side.
The spectra would still just be a property. I mean, you would still have the spectra from shadow trajectories, right? Because that's just an ergodic property.
So the spectra shows you that you're matching the solution at half the resolution. So if you basically, this has an effective resolution that is twice as high as the.
Ergodic properties, but that's not necessarily meaning that it's a real trajectory, right? So if you're going to show me the trajectory, though, can you prove to me that trajectory is not one that is still within the regime that has gone non-chaotic, right? So do you have a form of uncertainty quantification like province?
No, we didn't have that yet. So we're developing an OMIP now, which is like a global simulation. You have to look at the mean and the statistics of all this system, and we wanna test this hypothesis in this case. So we wanna do a global simulation at 1/6 of a degree and 1/12 of a degree using both the methods and see. Well, the idea is that this simulation should match this one at half the resolution. That's the hypothesis. And it has not been really completely verified yet, but we believe that that's what we're going to find.
Yeah, my point, though, is more so that, I mean, I agree with you, the higher order numerics is going to give you more exclusion, and it's going to be better than the ergodic properties, right? But showing two different trajectories and saying that they're, oh, hey, look how different they are. I mean, even if you just have a Lorentz equation, and you just change the tolerance of a time stepper from 1e minus 12 to 1f minus 12, right? So you just change the numerical accuracy of the tolerance that you're choosing. You will still have a gigantic difference in the trajectory. You'll say, oh, hey, look.
For sure, but
Looking at the trajectory, I mean, the graph.
I know. This is just a visual representation of the fact that that's diffused and that's not. There's clearly some more diffusion up there than down there.
Yeah,
right?
but it's hard to know whether.
Of course, you need more.
Either of those trajectories is really the true trajectory, whether it's just like another trajectory of the candidate system.
Of course, but the idea is just to visualize the fact that that's more diffusive than that one, which is visualized kind of from these pictures. Then we need to do more in-depth analysis for sure.
But this is also a snapshot, right?
Yeah.
This is also a snapshot.
Yeah.
How long did you run this for?
Um?
How long did this is a snapshot?
Yeah.
How
Yeah.
long did you run?
This was run for 20 years, I think.
20 years. So this is a snapshot that you're looking for.
No, yeah, for sure. For sure, it's not complete. It's not complete evidence.
All snapshots from a chaotic system, unless you've done the numerics set to a level of like 5,500 digits of accuracy, they're all random, right? And so saying like, oh, there's a big difference between these two methods. I'm like, I agree that there's a difference, but
So I can show you the fact that there's more kinetic energy down there than there, because that is more diffusive and there's a viscosity that diffuses out the currents. That there's more small scale energy contained in the low one than the top one, because you're not diffusing at the small scale like you're diffusing there. Yeah. Mm. Mm. Because typically you use a viscosity, right, to diffuse out numerical errors. Well, the viscosity in ocean models is really just a numerical gimmick, because you have numerical errors that you want to smooth out, otherwise the simulation will crash, basically. And this is what they do when using dispersive numerics. You use a dispersive scheme and a viscosity that is kind of like that, estimated from physics, and it's typically overly diffusive. So you cannot resolve. This is all undersolved, right? So if you continue increasing the resolution, you're going to have more and more dynamics for sure. Like, this is not representative of the complete physical dynamics. So what typically they do in ocean models is they put the viscosity that completely smooths out the currents, right? And that's what I mean when saying you want to try to increase your effective resolution. You want to have a method that doesn't diffuse, but still does not propagate dispersive errors, right? Yeah. Mm. Yeah. Mm. Mm. Yeah. Uncompared, yeah. Mm. Mm. Yeah. Yeah. For that, I'm a little bit more. I'm not sure, because you have to have also like correct ball formula, correct forcing, and this was kind of an idealized simulation. So we're working towards that validation, let's say. Mm. Mm. Yeah. 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 Okay, well, I guess I'll finish here with some nice visualization that show all the range of stuff that we can do with oceanography and ClimaOcean. Regional hydrostatic simulations, not really, because we're missing open boundary condition, as I was saying, but we're working towards that. Thank you. Any questions? Yeah.
I just want, because it's very impressive, I think, it's very promising too.
Mm-hmm.
My question is sort of very concretely kind of, how big of a team would you like to have working on this? Like for like...
I think we need more people. We need, I think, 2 or 3 more developers, like core developers, people that really wanna dive in the code and maintain it, and that's probably what we're missing. Mm-hmm.
So you make use of kernel abstractions, and one of the nice parts of kernel abstractions is that we can get really abstracted kernels. You said GPU, but I'm curious as to whether you played around with other GPUs. Like does this work directly on AMD GPUs and Intel GPUs, and can you run it on your Apple Metal as well, or do those require?
Yeah. Metal. I want to tackle that issue. The problem is that we have littered somewhere in the code some float 64s.
Oh, okay.
Yeah, so Metal is a little bit difficult. I have to trace back where that float 64 is to make it fully compatible with Metal. With AMD, it's compatible. It works. Just AMD is very slow compared to NVIDIA. It's crazy. Yeah.
Intel GPUs, no one even owns them. But it's just
Right.
curious to see whether
Right.
actually just the compilation process is kind of
Yeah, it works. I mean, there's a couple of tweaks that we have to do to make it work on AMD. So there are a couple of PRs open, but we never really merged it because we don't have testing pipeline for that. So we don't really want to merge capabilities for AMD. And for Metal, I would really love to have it, but I really have to trace back where these float 64s are. Mm. Mm-hmm. Okay.
The
Okay, we have 20 minutes. I'm getting there. All right. Okay. All right, so I was planning to go a little bit longer than 20 minutes, so I'll probably rush through this a little. The sort of the overall message of this presentation is about, we've talked about individual models and workflows and yesterday we also touched a lot on composability in the case of what JuliaEO is doing. We need to talk to that as well, but from a somewhat different perspective, because in what we do, as you've already heard, there's a lot of files and fairly long calculations. So the composability often comes with like, okay, I'm going to download one data set and I'm going to do a simulation, I'm going to save this and blah, blah, blah. So it's going to feel different. But this is sort of, I think, where we are in building kind of a composable ecosystem to make more complicated workflows in Julia, at least in my case. Alex also talked to that before, and the other Alex as well. So I'll say a little bit more about climate models and MIT-GCM-GL as promised, and then I'll get to the climatology-GL side of things, which is really on the data. I've already shown this. Climate models GL is a general interface that's really using files as a kind of a beginning point and an end point. It integrates various models that you can run that are somewhat light, MIT-GCM in particular through MIT-GCM-GL. I've already said this, there's interactivity coming from Julia. I wanted to illustrate a little bit what the interface is in practice. It consists for a given model, giving it 3 methods. One is called setup, the second is called build, and the third launch. With a shortcut, which is just run. So ultimately, you take one of those models I've mentioned, you do the first line here, which is defining a data structure and kind of telling you what the model actually is, and then you do run model, and you're done. So that's the goal, is to have some kind of 1 line, 2 lines, I guess, workflow. Setup typically is I'm going to deal with files, I'm going to choose a configuration and so on. The build, in the case of a Julia model, well, that happens on the fly, so maybe there's not even a build step, right? It's just like once you instantiate it in memory, it just happens for you. In the case of MIT-GCM, there's an actual, Fortran compiler that kicks in. And launch is really either run the thing, like do the calculation, or send it to a queuing system when it's bigger. What you see at the bottom is the run directory at the end of this, where you will find the output files, and then this log folder, which is where I keep track of the workflows. Here's a slightly different example where I do 2 simulations. So again, the first one defines a model, and this is this is a very, very simple model. This is like a random walk in Julia, so it's like a single function written in like 1 line. But it's just to demonstrate the strategy. Oh, my laptop is about to go down. Sorry, I need to check on, okay, I have 10%. That will keep us on time for lunch. Okay. So here what I do is I do the same simulation, okay? There is 100 step, and then want to modify that, do twice as long. So I change this in memory in Julia, right? That's one of the idea of this framework, is to expose the runtime parameters and the ones you care about out of the gazillion we might have. In memory, in Julia, you just change them and you hit run again, essentially, through this put and launch method. And then there's this log function. So what happens with the log part is each of those steps is put into a Git subfolder called log that you can then retrieve afterwards to know what you've done and to make the different workflows reproducible. So here you see that originally we did the setup, we put all of the parameters in a TOML file, built our sort of project, and then yep. Oh yeah, thank you. Oh, this is great. You should be able to, yeah. Yeah, thank you so much. So the point of this is, this is a very simple case where arguably there's a bit of an overhead with all of this, right? But often when we do modeling, we kind of explore things, we make decisions, we, trial and error type of thing. And so with this, I'm able to record that in an easy way, share it with somebody else, and that's meant to make my workflows reproducible. The same thing happens with a bunch of different models. Like I said, we don't always run the models. Right? In the case of IPCC models, for example, there is something that a lot of people do, which is I'm just going to get the output and do my calculations with that. I tend to call that the replay mode of climate and ocean models. And so that's why this fits right in. Of course, there is no build at this stage. So this is an example from the Climate Model Archive. I have built this sort of things for various models in different languages. Here is an example of a fast emulator of a big climate model. This one is called Hector. That's been created in C++ and sort of trained on the big models. But it's kind of nice because you can create scenarios like this, which can then become part of your workflow. So for example, what I would do with this is I create a future scenario, I can combine it with an existing ocean model solution and make predictions and kind of downscale to make scientific analysis. So that's climate models GL in general. I just want to give you a little bit more of a flavor. I've done some presentations before on this. Here is a little bit more detail on MIT GCM GL. So on the left is the, I guess, 3-line version of my running a GCM in Julia, in the case of the eco solution. So these are not the high-res models we've seen. It's the 1-degree configuration of MIT GCM that we use for the reanalysis. That runs on like 96 cores over 12 hours or something. The 3 lines on the left, that's just running the default, right? The reason I'm showing you this is mostly to show you the right-hand side. So the right-hand side is, using MIT GCM, blah, blah, blah. The first 3 lines is the same as before. Forget for now what's in the boxes, then setup, build, and launch. So same as exactly as before, but the reason I'm showing it is there's boxes in the middle where we're now going to modify what MIT GCM is doing. For example, we are going to say, well, I've already built this thing, so I don't need to recompile every time. So I can provide the link to the executable. I have a lot of input folders, like the same as Simone was telling you about. You need a bunch of forcing fields and a bunch of bathymetries and stuff. You don't want to download that every time. So typically you download them, you put them somewhere, and you just specify that. Then, you might want to modify the model runtime parameter. So not everything in a big model is changeable, right? You typically are not going to change the way that you discretize the world every time. That's kind of hard-coded. But there's a lot of things that are changeable at runtime, both in something like Oceananigans and something like MIT GCM. And so this is an example where I'm turning off a module. So those lines are all commented, but you uncomment them, and now you have an interactive way of making new solutions. I'm going to skip this, but I guess what this will point you to is a bit more of a detail on how the different configurations are kind of encoded in Julia. That's the first thing. the way that I'm dealing with all of my runtime parameters, this sort of monolithic thing leads to, I guess I'll show you this one. Right. So these are all of my runtime parameters that I change in this particular model. Right? This specifies all of the output and so on. So it's a long file indeed. Could calculate monolithic, that'd be okay. At least it's a toml file now. It used to be this kind of custom, annoying format that we had. So now I'm dealing with this way, and then the other bit was, ooh, where did this go? No. No. There we go. The last thing is, so MHECMGL generates a submission script for you at this point if you're going to use a queuing system. And so that's how you don't have to interact with that either. I'm going to skip over. The composability of this, I've already talked about. Here is an example where we run MHECM in an atmospheric configuration, and then on top of that, after that, we run a particle tracking simulation. Let me talk about the data side of things. So ocean modeling, in my mind, is mechanistic models, like the ones we just talked about, that have equations encoded in them and then simulations. But a lot of ocean modeling is also applying statistical methods and building statistical models or empirical models and training surrogates and all of that stuff, right? And so that's where you really want to start to have like input and outputs and deal with a lot of data sets. So I'll show you a couple of those workflows that I've been building with the same tools as before, but then adding data and adding different things to it. And they're rooted in my science, as always. So I'll go and refer you to this first example. So there is a warming of the ocean that's going on over the past decades. The second project is also about that. Here you're looking at, as a function of time and latitude, the change in SST, sea surface temperature, over 40 years. And you see this gradual warming all over the planet. The top is what data set that is from satellite. The bottom is one of my climatology MIT-GCM-based estimates. And so one of the reasons that we want to use mechanistic models is ultimately we want to attribute these kind of things. So we want to have heat budgets. So that's why when I do analyze these topics, I start from something like ECO, MHECM, that has a heat budget where the terms add up to 0. So in this plot, you're seeing the net change in temperature, essentially, in blue, for the layer between 0 and 200 meters. It's called ocean heat content because it's integrated, so it's in weird units, but essentially the change in temperature over that layer. The orange line is what comes from the atmosphere, and the green line is what crosses 200-meter depth. So that's what you need to have to be able to explain what's going on in the blue line. If you don't have those terms, and you just have temperature, we really don't have a good insight into the processes. So I always start from that, but then I want to make sure that I'm on track with observations as well. So that's when I bring in Argo again. This data set that I was telling you about is the key to monitoring ocean heat content. And so here is a comparison that just shows that the red line is kind of in agreement with my blue line, which is what's on the left-hand side from the model, or the mechanistic model. So that's the first thing. And then it does show that over this 0 to 200-meter layer over the past 20 years, there's indeed an increased accumulation of heat. So now we have a mix of different models that lets us really probe the behavior of the real system with some mechanistic understanding. Here's the workflow around this. And that's where it becomes really, building blocks and like accumulating steps that, some of them take a fair amount of time. So first off, I started with a 20-year solution, so I wanted to extend that to more like a 60-year solution, so I get an entire atmospheric analysis for this, download that, put that on some file folders. Then I'm going to use this to modify my solution and extend it in time. So these are the next 2 lines. I'm going to apply a first adjustment, which is because the model has run longer and was less optimized, it has drifted. So I'm recalibrating in timing towards echo, which is the reanalysis, the ocean reanalysis I was telling you about. And then I did 2 more corrections, adjustments. One, and they're both based on Argo and geospatial statistics of them. One is climatological and the other one is time variable. And I'm presenting all of this to you because that's where I wanted to get to, the geostatistical part, which relates to a lot of what we talked about. So this is what I do. I have my sparse data sets, Argo. I compute misfits, and I'm going to map the difference between Argo and the previous estimate, the intermediate step. Split up the world into boxes like this. So there's 30 of them in this case. That's the first level. You don't see the 30 of them because it's kind of a bit hard to read, but there's 30 of them. Then I do the same thing at twice the resolution. So here is, I've kept the color bar at 30 to see the increase in resolution. So this is my level 2, and I keep going like that. I keep making smaller and smaller boxes. So this is my level 9. If I only show you my 9th level of the multi-grid approach, if I just show you the first 30. In reality, there is like, at this point, something like 510 to the 5 boxes. So I'm computing these statistics, these sample means, like at varying resolution going down, and then I bring everything back, and I combine them into one big map. The Lancy mask is what? Oh, yeah, so that's because I do some interpolation for the plotting. Because it's on my weird grids that I was telling you before. The boxes? Well, it's pretty flexible. What I do is I start with, separating ocean basins, because I don't want to mix up, say, across the, the Pacific and the Atlantic, across Central America or something like that. And then I can choose whatever I want. So what I'm doing right now is pretty simple, but ultimately you can think about combining more like physically based, using the geometry of the gyres, things like that, and then downscaling with just basic ranges. But so I thought I would show this because it sort of it links to some of the discussions we had earlier in the week, and I'm hoping to engage some of this community in helping me advance these sort of things and make them faster or better, and that's kind of where I was. So that's one of the workflows that I've been building that is both combines a lot of different steps already and is relying on a lot of the JuliaEO kind of contributions, and we'll do more of that, so I'm hoping to get and to find some of you to help me on that. Another very related problem that I'm working on with my group is marine heat waves. So marine heat waves are a slightly different view of this warming in a sense, and you've heard of this over the past few years that we're finding more and more extremes. Or they're more intense, or they're more widespread, or they're more frequent. Some of that is a bit fudgy. So when you say increasing, there's some scientific discussion to have. But so it starts from this kind of a map of SST. This is the anomaly in sea surface temperature from satellite, and you see these big red blobs. That's what we're talking about. So the goal is going to be to isolate those things, track them through time, understand why they occur, and how they might evolve in the future based on our mechanistic understanding. But along the way, there's a lot of data analysis. And so the first thing is a time series bet. You take a time series like this of these SST anomalies where we've subtracted the climatological mean for every month, And you see that, you know, the red is above a certain threshold. We are passing it more and more. So yeah, you know, this was a marine heat wave, maybe. And now we have a lot more. So we start with that. And then, well, if you do that everywhere, you're going to find patches. And now you're going to want to keep track of those. Oh, this is not the right slide. Sorry. Oh, okay. Well, that slide never materialized. Sorry. It must be the wrong version of this talk. So in brief, the workflow looks like this is step 1 and step 2. Step 3 is this. You go from that to a polygon. And this is where something like geometry ops comes in. Then you want to do this sequentially for like every day. You want to overlap the polygons, decide if they are the same event, build a kind of a time variable moving polygon. Once you have that, then you can start studying it. So it's the state of affairs. I wanted to show this because I'm going to need help on that as well. But it's already been great to be able to leverage the Julia ecosystem for this. And I think we are going to do very nice things in this field. It's a nice use case to work on. If you're interested in contributing, please reach out. And since it's lunchtime, I'm going to go very briefly on this slide just to say there is still a need to consolidate the kind of the data accessing and handling ecosystem that we have. There's a lot of nice things that have been done to a large degree by this community. Things like the StackGL, for example, is very useful. I've created this DataVerse.jl package that interfaces with a data archive for now through its API to download and query, but then we should be able to push it as well. So the idea is, you know, at the end of your workflow, when you have your data set, you want to push it to an archive like that, put a DOI on it, right? And then your user needs to be able to download it automatically. So that's what DataVerse.jl is. I don't have time to talk about all this, but that's a very interesting project. I'm always, you know, excited to add more models to the climate model GL sort of world of things. Typically means, you know, taking shenanigans with the kind of API you have and bringing it back to the kind of APIs you don't like, that I do, but that a lot of people know. So I think it's a useful thing to do because it exposes the models that are innovative to the community that is not quite used to that, but it's an easy entryway to them. And it makes everything kind of interchangeable, such as, you know, when I want to use ClimaOcean, instead of MHDCM, I don't have to think about the APIs. At least I have a first way to do it. I was pretty excited with the talks on emulators, and so I have 2 candidates here that I think are ripe for putting into the JuliaSim world and that I've listed. There was also some very interesting stuff that I learned this week about existing interfaces to models, these FMIs and BMIs. And the last thing down my list is I'm still hoping we integrate more this kind of view of the geospatial analysis that's standard with the ones that we have in our sort of ocean modeling world, which, as you saw, has these weird kind of grids that don't necessarily always fit into the pre-existing models, but I think there's a lot to gain by tightening that up. And so, you know, if you're interested in that, please talk to me. Enough from me. Thank you for your attention. Sorry if it was a bit rough around the edges, these presentations. And if you have questions, please ask them. Thank you. Yeah. It's here.
So thank you, Gail, for this really good presentation and for organizing this this day actually. But the series in the morning was very interesting, and the afternoon is going to be full of a lot of action. So we have 4 hands-on sessions in the afternoon, 3. So we're going to have tracking ocean currents with MIT GCM, drifters, JL, regional ocean modeling with ROMS.jl, oceananigans.jl, and climateocean.jl. And so we're not having the session with emulators.
I've updated the agenda.
Well, okay. Okay. So meet us in an hour if you are online, and we can have lunch as normally across the wall.